What if I told you that the derivative of the inverse cosine function has one of the most intriguing formulas in calculus? Watch as we transform the graph of cosecant inverse x into its derivative right before your eyes. Now watch the magic happen as this function transforms into its derivative. Here's the exact formula we just visualized. The derivative of cosecant inverse x equals -1 over the absolute value of x times the square root of x squared minus 1. In the next few minutes, I'll break down every single component of this formula step by step, show you exactly where it comes from, and make it crystal clear why each part is essential. The inverse cosecant function, written as CSC inverse x, is one of the 6 inverse trigonometric functions. But what exactly does it mean? In mathematical terms, if y equals CSC inverse x, then the cosecant of y equals x. This is the fundamental relationship that defines the inverse cosecant function. However, the inverse cosecant function has important restrictions. Its domain is all real numbers x, where the absolute value of x is greater than or equal to 1. This means x must be less than or equal to -1 or greater than or equal to +1. The range of CSC inverse x is from 0 to pi over 2, excluding pi over 2, combined with the interval from pi over 2 to pi, excluding pi over 2. This ensures that each x value corresponds to exactly one angle. Why do we have these restrictions? Remember that cosecant is 1 over sine. Since sine values are always between -1 and +1, cosecant values are always greater than or equal to 1 in absolute value. On the unit circle, we can see specific examples. When sine equals 1/2, cosecant equals 2. When sine equals -1/2, cosecant equals -2. Notice how cosecant values are never between -1 and +1. This is why the domain of CSC inverse x requires the absolute value of x to be at least 1. The inverse cosecant function takes these restricted cosecant values and returns the corresponding angles within its specified range. Here is the derivative formula for the inverse cosecant function. The derivative of inverse cosecant of x equals -1 divided by the absolute value of x times the square root of x squared minus 1. Now let's examine each part of this formula to understand what makes it work. We'll break it down into its key components. First, we have the negative sign. This is crucial because it ensures that the derivative is always negative, which tells us that the inverse cosecant function is decreasing throughout its domain. Next, we have the absolute value of x in the denominator. This absolute value is essential because the inverse cosecant function is defined for both positive and negative values of x, specifically when x is greater than or equal to 1 or less than or equal to -1. Finally, we have the square root of x squared minus 1. This term is only defined when x squared minus 1 is greater than or equal to 0, which reinforces our domain restriction that x must be at least 1 in absolute value. Now let's discuss the domain restrictions more carefully. The domain of both the inverse cosecant function and its derivative requires that the absolute value of x be greater than or equal to 1. This means x can be less than or equal to -1 or greater than or equal to +1. However, for the derivative specifically, we must exclude the points x equals +1 and x equals -1 because the derivative becomes undefined at these boundary points. Let's take one final look at our complete derivative formula. Remember, this derivative formula tells us that the inverse cosecant function is always decreasing. The negative sign ensures this, while the absolute value and square root terms handle the domain restrictions properly. This formula will be essential when we work through examples and applications. Now we're ready to derive the formula using implicit differentiation. This powerful technique will help us find the derivative step by step. Step 1. We start by letting y equal the inverse cosecant of x. This substitution is the key to setting up our implicit differentiation. Step 2. Now we take the cosecant of both sides. Since y equals inverse cosecant of x, then cosecant of y must equal x. This gives us an equation we can differentiate. Perfect. We now have our setup complete. In the next step, we'll differentiate both sides of this equation with respect to x. The chain rule will be crucial in our next step, as we'll need to account for the derivative of y with respect to x when we differentiate the left side. We're now ready to move forward with the differentiation process. Our foundation is solid, and we're prepared for the next crucial steps. Now we continue our derivation. We have established that y equals inverse cosecant of x, which means cosecant y equals x. Next, we need to differentiate both sides of this equation. Step 3. We differentiate both sides of the equation, cosecant y equals x, with respect to x. We apply the derivative operator d dx to both sides. On the left, we have the derivative of cosecant y, and on the right, we have the derivative of x. Remember the key trigonometric derivative. The derivative of cosecant u equals negative cosecant u cotangent u times du dx. This is a fundamental derivative we must memorize. Applying this rule to our equation, where u equals y, we get negative cosecant y cotangent y times dy dx on the left side. The right side simply becomes 1, since the derivative of x with respect to x is 1. So we have negative cosecant y cotangent y times dy dx equals 1. Step 4. Now we need to solve for dy dx by isolating it on one side of the equation. To isolate dy dx, we divide both sides by negative cosecant y cotangent y. This gives us dy dx equals negative 1 divided by cosecant y cotangent y. Notice how we've color-coded the terms. The negative sign is now in front, and we have 1 in the numerator and cosecant y cotangent y in the denominator. We now have the derivative in terms of y, but we need to express this result in terms of x. That's what we'll tackle in the next part of our derivation. Now we need to express this result in terms of x instead of y. We have the derivative as negative 1 over cosecant y times cotangent y. Step 5. We need to express cotangent y in terms of x using trigonometric identities. We use the fundamental trigonometric identity. Cotangent squared y equals cosecant squared y minus 1. Taking the square root of both sides, we get cotangent y equals plus or minus the square root of cosecant squared y minus 1. Since we know that cosecant y equals x, we can substitute to get cotangent y equals plus or minus the square root of x squared minus 1. Now we need to determine the correct sign. This is where the range of the inverse cosecant function becomes crucial. Step 6. We must determine whether to use the positive or negative square root based on the range of inverse cosecant. The range of inverse cosecant x is from 0 to pi over 2, excluding pi over 2, union with pi over 2 to pi. In this range, cotangent y is always less than or equal to 0. This means we must choose the negative square root. Therefore, cotangent y equals negative square root of x squared minus 1. Now we can complete our derivation by substituting this back into our derivative formula. Step 7. We substitute our expression for cotangent y back into the derivative formula. Substituting, we get dy dx equals negative 1 over x times negative square root of x squared minus 1. The double negative simplifies to positive, giving us 1 over x times square root of x squared minus 1. However, we need to account for the domain restriction. Since x can be negative, we need the absolute value of x in the denominator. This gives us our final answer. The derivative of inverse cosecant x equals negative 1 over the absolute value of x times the square root of x squared minus 1. Notice the negative sign, the absolute value of x, and the square root term. Each component comes from our careful analysis of the trigonometric identities and domain restrictions. We have successfully completed the derivation using implicit differentiation. The key steps were expressing cotangent in terms of x, choosing the correct sign based on the range, and carefully handling the absolute value. Now let's apply what we've learned to solve a concrete example. We need to find the derivative of the inverse cosecant of 2x. This will require the chain rule since we have a composite function. Step 1. Since we have a composite function, we need to apply the chain rule. Let's set u equals 2x, so our function becomes the inverse cosecant of u. Step 2. Now we need to find du dx. Since u equals 2x, the derivative of u with respect to x is simply 2. Step 3. Now we substitute into our derivative formula. The derivative of inverse cosecant of u is negative 1 over the absolute value of u times the square root of u squared minus 1, and we multiply this by du dx, which is 2. Step 4. Now we substitute back u equals 2x into our expression. This gives us negative 2 over the absolute value of 2x times the square root of 2x quantity squared minus 1. Step 5. Finally, let's simplify this expression. We can expand 2x squared to get 4x squared, and we can factor out the 2 from the absolute value in the denominator. This gives us our final answer. Negative 1 over the absolute value of x times the square root of 4x squared minus 1. Perfect. We've successfully found the derivative of inverse cosecant of 2x using the chain rule. Notice how we carefully applied each step, identifying the inner function, finding its derivative, and then simplifying our final result. This systematic approach works for any composite inverse trigonometric function. We've covered a lot of ground today. Let's recap the key formula we derived. The derivative of inverse cosecant x is -1 over the absolute value of x times the square root of x squared minus 1. Remember the three key steps in our derivation. First, we used implicit differentiation starting with y equals inverse cosecant x. Second, we applied the chain rule and trigonometric identities. Third, we carefully handled the absolute value and sign considerations. Now let's address the three most common mistakes students make with this derivative. First, forgetting the absolute value around x. Second, getting the wrong sign. Remember, it's negative. Third, ignoring the domain restriction that x must be greater than or equal to 1 in absolute value. To master this topic, I encourage you to practice with more examples. Try finding derivatives of compositions like inverse cosecant of 2x or inverse cosecant of x squared. Each practice problem will strengthen your understanding of the chain rule and domain considerations. If you enjoyed learning about the derivative of inverse cosecant, check out my other videos on derivatives of inverse sine, inverse cosine, and inverse tangent. These functions all follow similar patterns, but have their own unique characteristics and applications. That's a wrap on the derivative of inverse cosecant x.